serious here. All right, our next talk is from Sam Hopkins at Berkeley. Are there information computation gaps unique to and in high probability heavy-tailed estimation?
Yeah, thanks, Chris, and all the organizers. This talk is basically going to be a 25-minute infomercial for an open problem or open direction that I think is interesting and understudied. That is, it's going to be about some recent work, which I think hints at the potential existence of a kind of information computation gap that we haven't really seen before, to my knowledge. So this is based on joint work with Yeshwanth, Tarun, Prasad, and Nilesh here at Berkeley. So the game that we're going to be interested in is high probability estimation in high dimensions. So for statisticians, this is estimation where we pay attention to confidence intervals. So the game generically, abstractly, will be this: given some number n of independent samples from some high dimensional probability distribution p theta, parameterized by some parameters theta, estimate these parameters theta by some theta hat, which is close to theta in some norm, where close is measured by some number that I will call the rate, the error rate. And we'll think of a rate as depending on the number of samples, the ambient dimension of these samples, and the probability with which we are willing to fail. So this R rate is also the radius of a 1 minus delta confidence interval. Of course, in the real world, you might want this to depend on more things like some geometry, some underlying geometry of the problem you're considering. But to keep things simple, we'll just think about number of samples, dimension, and confidence level. And we're going to be interested in what happens when you try to do basic estimation problems for very large classes of distributions. I will try to make the weakest possible assumptions on the distributions in question. Like maybe I would like to allow p theta to be any distribution with a small number of bounded moments. And this is in contrast to the kind of assumptions that one often makes when analyzing confidence intervals. One often assumes Gaussianness or sub-Gaussianness, which is a much stronger kind of assumption. But our goal will be to match the kind of guarantees you would get if you were working with Gaussian distributions, but drop strong assumptions to be much more permissive in what kind of distributions we can handle. So let me illustrate with maybe the two most basic problems in high dimensional estimation. One is estimating the mean of a random variable. So that's, in this case, the norm we'll consider will just be L2, the Euclidean norm, and the parameters we want are just the expectation of the random variable. And the second is covariance estimation, where my goal is to estimate, let's just assume the mean is 0, so that you're really just estimating the second moment. You want to estimate the covariance, and the norm I'm going to be interested in is operator norm, maximum eigenvalue, maximum magnitude eigenvalue. Just as some bookkeeping, so that I can make it a bit easy to write things, for this talk, all the distributions that I will consider will have covariances that are kind of very loosely approximately identity in the following sense. Their trace should be like some constant times the ambient dimension, and their maximum eigenvalue should be some constant independent of dimension. This is not needed for any of the theorems that I'll say in the talk, but it makes it easier to kind of compare things quantitatively. Okay, so these are my two problems, two most basic problems in high dimensional estimation. Let's talk about the state of the art. Oh, I meant to clear this slide. So I gave away my own punchline here, but that's fine. So I'm going to define some magic number called R star. And R star is going to be the confidence interval rate, which shows up for a whole bunch of different settings. It's some very fundamental quantity. It's the square root of ambient dimension divided by square root of number of samples plus square root log 1 over delta over number of samples. So sorry, I meant to fill this slide in live, but I'll just highlight live. So the first question is, what if let's think about my benchmark case, which is Gaussian distributions. What if I want to do the simplest thing in the world, which is estimate the mean of a Gaussian distribution in high dimensions with confidence intervals? Well, if you just do some standard concentration applied to the empirical mean, which is the best estimator, you will find that this is the confidence interval radius that you get. And this estimator can be computed in polynomial time. It's just the empirical mean. So this is our benchmark for estimation of the mean. Now, what if you want to drop a Gaussian assumption? Now the empirical mean is not a good choice. The empirical mean is not robust to the kind of fluctuations that you would see if you wanted to make a much weaker assumption, just like a constant number of bounded moments in your distribution. It turns out, though, and this is only understood quite recently, that at least if you are willing to expend exponential time and go beyond the empirical mean as your estimator, you can compute some kind of a high dimensional median, some relative of the Tukey median, and you can maintain up to constant factors this confidence interval radius R star. This is due to Lugosi and Mendelssohn from 2018. And high dimensional medians, however, are notoriously hard to compute. The Tukey median is hard to compute in the worst case. This is some relative of it, so one might be worried that this would be strictly theoretical in the sense that you wouldn't be able to give a polynomial time analog. But it turned out that actually in the case of estimating the mean in L2, it is possible to do it in polynomial time and still up to constant factors preserve this optimal confidence interval rate R star. So here in this talk by polynomial time, I usually mean polynomial in n, d, and log 1 over delta. So this is a result from 2018. And that means, of course, you can do it in this slightly slower running time and poly nd 1 over delta, which is more than slightly slower. It's exponentially slower with respect to delta.
Hey,
so what
Sam,
this means, yeah.
The high dimensional median is the thing which minimizes the sum of the L1 distances to all the data points. Is that right?
Not in this case. That's a good question. So I'll show you actually the analog of the median I'm interested in for covariance estimation. It's something more complicated than that. The thing that you just, there's no canonical high dimensional median. Actually, the one you just described is often called the geometric median. The Tukey median is slightly different. In this case, what one wants is any point which is close to a majority of the samples in every univariate direction, in every univariate projection. So this is again different from geometric median. Yeah, so geometric median actually will not get you this guarantee. In the case of covariance, so what this means is that in the case of estimating the mean, everything has a nice kind of bow on it. You can do information theoretically optimal estimation in polynomial time. What about estimation of the covariance, the next most interesting, next most sophisticated high dimensional estimation problem? Well, almost the whole story is the same except the ending. So in the Gaussian case, if you just use empirical covariance in the parameter regime that I'm talking about, again, you'll get this exact same confidence interval radius. This is kind of an accident. It's just because of the way I set up the parameters, but you'll get some optimal thing for Gaussians. This is, of course, doable in polynomial time because it's just the empirical covariance. In exponential time, if you just assume something about fourth moments, you can match this using, again, some kind of pretty sophisticated high dimensional median. It turns out that if you're willing to run in time polynomial in n and d, but exponential in log 1 over delta, which is to say polynomial in 1 over delta, then you can still match this. This is a result of ours from earlier this year. But I have no idea if you can match it if you want truly polynomial running time, poly n d log 1 over delta. So this is the open problem I'm advertising for this talk, and let me try to make the case that it's not just some technical thing, that there's something qualitatively interesting going on here. So the open problem is, can you design a polynomial time algorithm which takes independent samples from some distribution where you make only assumptions on a few moments of that distribution, and gives an estimate theta hat of its covariance such that theta minus theta hat in operator norm is small, where small means this optimal quantity, the thing you would have gotten if you were working with Gaussians. I actually think there's a good chance, and we'll see why later in the talk. I think there's a good chance that this is actually not possible. And if it's not possible, the other half of the open problem is to give some kind of rigorous evidence that no such efficient algorithm exists. And this is where I think something qualitatively different is happening. This would be rigorous evidence for an information computation gap that has to somehow isolate the small delta regime of estimation. It's supposed to apply only to very high probability estimation. Notice that even if I make only a small number of moment assumptions, the empirical covariance still does a good job. It still does the right thing for large deltas. This really contrasts with something like planted clique or sparse PCA, where success probability of your estimator is not really affecting whether your problem is tractable or not. It's really about, sparsity level or number of samples. It also has to apply only to kind of highly non-Gaussian distributions. Again, not something we're used to when we're giving evidence for information computation gaps, because the empirical covariance would work just fine for Gaussian distributions, and that's of course efficiently computable. So I have no idea how to give rigorous evidence in this situation, but I think this means that if we could do it, it would be a qualitatively new kind of information computation gap. So
I have a question.
Yeah.
Does the answer to this question depend on the norm that you're choosing to measure the distance with respect to, like the operator norm versus the Hilbert-Schmidt norm, etc.?
Yeah, I think in Frobenius norm, okay, I didn't check this in detail ever, but if you're trying Frobenius norm or Hilbert-Schmidt norm, right, that's just like the L2 norm of some random vector, and that we know how to do from estimating the mean in L2. So this is really about getting the covariance right in a spectral sense. You could talk about estimating in Loevner order, or in relative PSD order. That would probably have this same issue. That's strictly harder than what I'm asking you to do here. And actually, that's a really hard problem. I don't know how to do that at all. Yeah, thanks. Does that answer the question? Okay. So in my remaining time, I want to sketch the current state-of-the-art algorithms for covariance estimation with when heavy-tailed distributions are allowed. Heavy-tailed meaning I only assume bounds on a constant number of moments. And I want to suggest, this is the hint of an information computation gap. It's at most a hint, but I want to show you why at least current techniques seem to face significant roadblocks to further improvement. But I don't believe these are yet fundamental roadblocks to any polynomial time algorithm. Okay, so to do that, let's return to the exponential time setting and just talk about these results by Lugosi and Mendelssohn and Zhivatovsky on some kind of very fancy high-dimensional median-based estimator for the covariance. So as before, the setup is going to be that I get n samples. They're d-dimensional vectors. They're from some probability distribution where I'm assuming something only about a few moments. And just for convenience, let me assume the expectation of that distribution is 0. So the first step in this estimator, actually in basically all the estimators in this area, this is very standard, is you take your samples and you put them into some buckets at random. Don't look at the samples before you do this. And you compute empirical averages within each bucket. So this is just some kind of variance reduction step. In this case, I take my samples, I put them into log 1/delta buckets. Turns out to be the right number if I want to think about confidence level 1 minus delta. And within each bucket, I compute the empirical covariance. So I'm going to call those empirical covariances Z1 up to Z log 1/delta. They are, of course, D by D matrices. And then we do something fancy. So now I have these Z's. They are independent, unbiased estimators of the covariance, but on their own, they're no better than the empirical covariance, right? They're actually worse. They don't give you high probability guarantees in the setting of just a constant number of bounded moments. So the amazing trick by these folks is to say that what you should do to combine these Z1 to Z log 1/delta is compute what I'm going to call a spectral Rcenter, although that's not what they called it, but I like this terminology better, which is a matrix M with the following property. And it's a bit complicated, so we'll try to take it a little slow. It's a matrix M such that for every unit vector V, for every L2 unit vector V, if you look at the quadratic form of your matrix M at V, and you look at the quadratic forms of these Zi matrices at V, the quadratic forms are close for a majority of the Zi's, okay? So a spectral Rcenter is one where close means distance at most R, and the estimator is find an Rcenter for the minimal R such that that exists. it turns out that that will exist for R equals R star, this optimal estimation rate. That's a non-trivial probability fact to prove. So pictorially, what's going on over here is that you've got these matrices Z1, Z2, Z3, and so on. And a spectral Rcenter is any matrix M such that when you project all of these guys in the space of D by D matrices onto a rank 1 matrix, that in this projection, M is close to a majority of your guys. In this case, it's close to 2 out of 3 of them that are within distance R.
So Sam, just to clarify, this is a little bit weaker than saying that it's close in operator norm to 60% of them, because which 60%
Yes,
change
precisely. Precisely. Which vector I choose here will change which 60% I might be close to. And that's creating all the algorithmic difficulty. Actually, just checking closeness in operator norm to 60% of the guys, not so hard. But that turns out not to be an approach which will get you the right guarantees. That will get you weaker estimation guarantees if you make that your definition of center. So this is a pretty sophisticated definition. It's not trivial to analyze, and it's pretty cool that, that these folks managed to do it and prove the following theorem, which says that if you use a spectral Rcenter, then up to logarithmic factors in D, you will get an estimator which in operator norm is optimally close with probability 1 minus delta, assuming only a bound on the 4th moments of your underlying random vector. So this is kind of amazing. You don't need Gaussianness at all. You don't need anything like it. You just need 4th moments. But of course, I like algorithms. And the question is now, can you compute an Rcenter, a spectral Rcenter efficiently? How on earth are you going to do this? Notice that even if I handed you a spectral Rcenter, it's not really clear how you would even check whether I give you M and check whether it is or is not a spectral Rcenter, because this definition, as Chris points out, involves some universal quantification over all rank 1 matrices, over all unit directions V. And without doing some brute force enumeration of those directions, I don't know even how to check that, that this M has the spectral Rcenter property. This is just to say, it's not clear how you would do this algorithmically. We are able to give some partial progress in this regard. So here's the theorem here. In polynomial time, we are able to design an estimator for high dimensional covariance of heavy-tailed distributions, which has this funny looking guarantee. This is the radius of its confidence intervals. And I've highlighted this term log 1 over delta to the 1/4, which is the amount by which we are off from optimality. So this looks crazy, I realize, and it looks like some bizarrely technical thing, but I'm going to give you some evidence in just a moment that this is at least close to optimal for the kind of techniques we're using. So just to read it out, our confidence interval radius is root d over n times log 1 over delta to the 1/4 plus log 1 over delta over over n all to the 1/2. And just to offer you some comparison, let me rewrite what you would have gotten in the Gaussian case. It's root d over n plus root log 1 over delta over n. We need to make an assumption, a slightly stronger assumption than Lugosi and Mendelssohn do. We need an assumption on 8th moments, and we need something called a certifiability assumption on those 8th moments. This is something Pravesh also alluded to in his talk. This is by now a sort of standard assumption in the robust and heavy-tailed statistics literature, but the normal situation is that when you make an assumption like this, you get information theoretically optimal estimators. And what's interesting here is that even with this kind of assumption, we still don't achieve information theoretic optimality. Notice, however, that we are still sort of faithful to our original goal, which was make assumptions only on a constant number of moments. We have achieved that. We certainly don't need Gaussianity or strong tail bounds or anything like that. So this is the main theorem. Let me tell you briefly about the algorithm and then what the roadblocks are to information theoretic optimality via our route. So our strategy is going to be to guess in some kind of lame way some initial estimator, and then compute a series of iterates until we arrive at our final estimator M. At each step of our iteration, we're going to attempt to certify that that my current guess, my current iterate, is a spectral R-center. And if I succeed at that, if I somehow determine that it is a spectral R-center, then I'll output it. I'm done. Life is good. If I fail, then I'm going to hope that my certification algorithm, when it fails, I'm going to hope that it produces some kind of witness to that failure. It tells me some direction where I got the quadratic forms of lots of my z's wrong. And then I will update my matrix in some way to fix those quadratic forms. So the picture is this. I remember that I want to be a spectral center of these matrices Z1 up to Z log 1 over delta, which were the results of putting my samples in buckets and computing empirical covariances. So if my iterate, the ith iterate is sitting over here, and there's some direction VV transpose where the z's actually all live over here, then I'm hoping that when my certification algorithm fails, it will tell me about this direction, and I will update my to this I plus first iterate along this line. So that's going to be the goal. And the key thing we need to make sure we can do is this certification step. Once we can design a certification algorithm, everything else is a reasonably standard analysis. And the key sub-problem in doing that is to show that if I gave you the truth, if I gave you the ground truth covariance, that you would be able to certify that it was indeed a spectral center of these random matrices Z1 to Z log 1 over delta. So we are able to design a certification algorithm which does exactly that for some choice of R, which is slightly suboptimal. In particular, it's off by this log 1 over delta to the 1/4 that I mentioned before, and that's of course the origin of the suboptimality in our guarantees. So we translate spectral R-centerness into some optimization problem. We relax that optimization problem to a sum of squares semi-definite program, and we analyze the sum of squares semi-definite program in the average case when the z's are these random matrices to prove this guarantee. This occupies, a great deal of technical work that the awesome students at Berkeley handled with aplomb. But let me point out once again that this is not optimal, and in fact you can view the difference between our algorithm and the exponential time one through this lens, because the ground truth covariance is actually a spectral R center for much smaller R. It's a spectral R center for this optimal choice of R. And if you could certify that, I expect you would be able to design an optimal algorithm efficiently. So in my final couple of,
Sam, Tim asks, does the 1/4 improve if you make moment assumptions beyond the 1/8?
Great question.
Assuming that you could do the SOS again.
I don't know how to do it. It might. A sort of reasonable kind of conjecture would be that if you made much higher, I really don't know. I sort of think the 1/4 might improve if you make higher moment assumptions and you go much higher in the SOS hierarchy, like degree d to the epsilon or something. There might be an avenue to improving things. We can talk about it later, but yeah, I don't know.
1/4 is kind of a natural barrier, you think, for like constant degree, let's say.
Let me give you the next slide, and then you can decide for yourself. So the obvious question that Tim is also pointing out is, can you do certification for smaller values of R? Right? If you could, then as I said, you probably would improve our guarantees. We offer some evidence that this seems hard to do the certification problem, and this is what I mean by evidence that current approaches don't seem improvable past this log 1 over delta to the 1/4. The evidence is in the form of a conjectured hard distribution for this certification problem. The hard distribution is some joint distribution of samples x1 to xn. They're not independently distributed anymore, such that in my joint distribution, if I do my bucketing and I produce my matrices Z, the identity matrix fails to be an R center for this value of R, slightly below the value that we're able to do certification for, log 1 over delta to the 0.24 instead of 0.25. But no polynomial of small degree, which I think we're going to hear a lot about this kind of evidence later, but no polynomial jointly in the samples of small degree is able to distinguish this joint distribution of samples from just a list of independent samples from normal zero identity, from Gaussian. But in the Gaussian case, the identity matrix is an Rcenter for much smaller values of R. So we set up some distinguishing problem, some hypothesis testing problem that we think is hard. We give some kind of mild evidence of hardness. And if this problem is hard, then you shouldn't be able to do certification for R smaller than we are able to do. That would suggest that the path to improving covariance estimation in this way is maybe closed. But of course, this doesn't say very much about the problem of heavy-tailed covariance estimation in general. Of course, nobody says you have to go at it via this spectral Rcenter approach or via certifying algorithms at all. So I will close with the high-level question that I opened with, which is, are there information computation gaps that are unique to the high probability estimation setting when you want very high rates of success, and unique to non-Gaussian estimation problems? So thanks very much for your attention, and let's do questions.
So just to make sure I understand, there was this more naive notion of an Rcenter, namely one which just has small spectral norm difference, so that it would simultaneously, sorry, from 60% of them, so that you wouldn't be changing which 60% depends on the unit vector.
Right.
And you're saying that the ground truth simply does not satisfy that for R star. I would have to throw in
no, it does satisfy that for R star. The problem is that lots of other matrices do too. And if that's your only criterion for picking a matrix,
but isn't this a stronger property?
Being close to 60% of them?
Because then it.
Oh, sorry. I see what you're saying. That's right. No, it does not satisfy it for R star. My mistake. My mistake. Yeah.
Okay.
Right. In fact, in most cases, these Z matrices, they'll actually be rank deficient, right? Like they might even they might even be rank, constant rank or something. In which case, their spectral norm to the distance to the covariance is very high, like a constant.
Alex Wine asks, is it easy to explain what your planted distribution is?
Yeah, it's not hard. I can actually do that really quick, probably. Okay, now AirPlay decides to freeze. What you do, Alex, is you put in, you like pick the buckets ahead of time. I'm just resetting my screen share here. Like you decide that, you look what buckets the algorithm is going to choose. Okay, so you assume that you can know those, and then what you do is, so you have your samples like x1 to xn that I want to create. Here are the buckets. And in half the buckets, what I will do is I will make them be samples from normal zero identity plus VV transpose for some V. And in the other half the buckets, I'll make them be IID samples from normal zero identity minus VV transpose for some V. Okay, so that if you look at the overall covariance of everything, it'll still look like identity, but there'll be this planted direction V. Okay, I have to put some, put the right scaling in it and everything. But there'll be some direction V where identity is actually far from any of the bucketed covariances.
But so are you? It seems like this is a distribution on the buckets. These are not buckets that could actually arise from the random bucketing.
Yeah. So you need, the algorithm doesn't have to do random bucketing. The algorithm can just put the first block of samples into the first bucket and the next block of samples into the next bucket and the next block into the next bucket and so on. But you're right that random bucketing would seem to defeat this this counterexample. As I said, this is like pretty mild evidence of a roadblock. It's what we've got, but I'm not saying it's terribly convincing.
So Andres, I'm no longer the host, but Andres has a couple of questions in the Q&A. Andres, you can unmute yourself if you want. Tim has a follow-up question about the 1/4.
So again, so the ground truth inference version of this is to think of, right, that there is a ground truth, and then you have n noisy teachers that have some unknown error covariance matrix. Right?
Yeah, I guess in the sense that each sample is some kind of teacher about the thing you want to estimate.
Exactly. For each, so for example, for x1, right, something comes down. It's an online kind of algorithm. X1 comes down the line, and the n noisy teachers are going to perturb it with some unknown error covariance matrix, right? So it's a different problem from what you're doing, right? But I'm just pointing out that in that one, right, you can actually recover it using these error moments algebraic equations, and you can only do it if for what I would call precision error, because you can't compute the bias, right? You have to demean the signal, if you will, of all the your noisy estimators. But that problem is solvable when, you know, they're sparse in their correlations of the errors that they make. Certainly when they're independent of the error on the ground truth, but sparsely correlated, they can be recovered. But as they become more correlated, then it's going to become unsolvable again. So again, I point out.
So I mean, right. It sounds like there's that in some other problem related, there are information computation gaps, and you know,
Exactly.
So the question here that I want to highlight, though, is whether there are gaps that especially emerge when you want to do very, very high probability kind of estimation. But I'm happy to discuss this further offline if you want. I'm around on the Discord, and you can find my my email online and things like that. We're short of time, so maybe we can go to Tim quickly, or Chris. Are we out of time?
Tim, are you unmuted now?
Yeah, I'm unmuted.
You'll be the last question.
Okay. I was just curious if there's some very like brief explanation or thing you can point to here that explains where this exponent 1/4 comes from specifically, rather than anything else. So it seems.
Yeah. Okay. I mean, I think for you, what I can say is that it's the same. This is not going to be so intelligible to a lot of folks, but
right, no, this is exactly. It's the same 1/4 as what?
It's the same 1/4 as like the n3/4 in tensor PCA, or the number of clauses to the 3/2 in random 3 XOR, because our certification algorithm goes via the same approach. We turn the thing into, you know, basically a 3 CSP, and then we do refutation on the 3s. It's not really a 3 CSP, but it's the same kind of random matrix structure, and then you do refutation on that.
Cool. All right. Thanks.
Very cool.
Well, I guess you lean towards hardness of this problem below the 1/4, right?
Well, for certification, I think it's hard. I mean, I admit there are some drawbacks to this hard instance, but I think for certification, it's hard. For estimation, improving the 1/4, I really have no idea. I'm neutral on it. I don't know.
All right, let's thank Sam, and so we will come back in 6.5 minutes for Amin's talk. Thank you very much.
Chris.